So if you recall where we left off last time, I discussed various aspects of the fork join pool and how that was used to run the different results that were created in chunks by the splitterator in parallel using the fork join pool. So everything's off and running, doing the fork join pool stuff. And we also talked about the issues about fork join pool size, the number of threads that are in the fork join pool. We talked about how to use a managed blocker to avoid starving the threads by having extra threads be allocated on demand. And probably a good metaphor for that would be, sort of seasonal workers at Amazon fulfillment centers or Walmart, right? You hire temporary workers to come in for a short time and do a few things, and then they go away after the busy season's over. So that's kind of the way that the managed blocker works for the fork join pool. It does stuff temporarily and boosts the number of threads, and then it goes away. Does everybody feel comfortable with why we want to add threads to the fork join pool, especially if you do blocking operations? What's the reason for doing that? Kelly. Right. So the answer is basically the following. If you have I/O-bound tasks or work, then when those things are blocked on I/O, like reads or writes, and in a case like an image crawler, it'll probably spend a fair amount of time blocked in I/O, downloading the images, if they're large, especially from the web, and maybe even doing some other operations like writing the output after you've transformed it or so on. After those things, while those things are going on, the thread will be blocked. And if you only have a fixed number of threads in the pool, like let's say 4, and you've got a large number of downloads going on simultaneously, like 28, which is the case with the completable futures version of your assignment, then what you'll end up with here is a situation where all those threads will be blocked in I/O. There's plenty of CPU to go around because when a thread is blocked, it essentially relinquishes the core because it's blocked, and the operating system puts that thread to sleep till it's finished downloading the work. And at that point, there'd be nothing else to do. So by having the ability to temporarily increase the number of threads in the pool, that allows other things to happen. So you could start other downloads, which might very quickly block. Or as things stop blocking, you could have threads that are off and doing various image transformation, image filtering, image processing operations. So the ability to keep the threads in the pool is essential to what's going on. Any questions about that? Okay, so what we're going to do now is talk about the next phase, the next stage in the stream's phases. Remember, there's the splitting phase, there's the processing phase. We talked about splitterators. We talked about processing with a thread pool. Now we're going to talk about the combining phase or the joining phase that's going to do what's called a reduction. And that combines all these partial results into a single result. And we'll also talk about something involved with collectors, both concurrent and non-concurrent collectors. And we'll see that the concurrent collector in particular behaves a little bit differently because it doesn't really combine partial results in a single result in quite the same way that a non-concurrent collector does. And I'll talk through both ways of doing things. It's really quite interesting. But first, let's talk about how you combine results in a parallel stream. So after the common fork join pool finishes processing the chunks, and actually it's not after it's finished processing them all, it's as they finish or as they're finishing, the partial results can be combined into a final result. So this kind of shows you an overview of how this looks visually, where you've got these different threads running in parallel. As they finish up, those things will then join the partial results. So obviously you don't have to wait for everything to finish till you start joining partial results. There can be joining taking place as things finish. And these are all the partial results. And of course, the piece at the very, very bottom is the final result. And the joining occurs at in a single thread at each level. This, of course, is kind of dependent on the concurrency model that's being used, and we'll talk more about that in a second. But essentially, the parent is going to be responsible for joining the children. And the main thing to remember here is there's no need for synchronizers during this joining. And that's because we're not joining two things in two different threads in the non-concurrent collector case. we're joining them in a single thread. Does that make sense? So it's like, it's kind of like people do work, and then they bring it and they drop it off, and one person puts it together. So there's only one person that's taking the results of the concurrent threads and joining them. And it's typically the parent that does that. And when we get a little bit further into the fork join pool implementation details, which I'll show you later, not this week, but probably next week, you'll see how this all works. There's a parent that forks things off and then waits for them to complete and joins them back together again. So there's always a kind of a master that's putting all the various pieces back together. Now, this is, the next discussion is a little bit subtle, and it's interesting how confusing it is. And if you read articles about streams and parallel streams, a lot of people get this wrong. So I'll try to explain it carefully. And the thing that makes it complicated is that there's a number of different things that might differ and vary, and you have to keep track of which one is going on at any given point. So different terminal operations combine the partial results in different ways. And for sequential streams, it doesn't really matter, right? Because there's only one thread of control, so what's the big deal? For parallel streams, it makes a big difference. And so you have to really understand what I'm about to talk about when you're dealing with parallel streams, which of course is the interesting part of all this. Streams are fun, but parallel streams are really fun. So the couple different alternative ways of doing things are reduce and collect. So let's talk about reduce first. And reduce is a reduction operation, obviously, by its name. And it creates what's called a new so-called immutable value. And that means that it's going to be something that doesn't get updated. Once it's created, it has its value and it doesn't change. And if you recall our whole discussion about the hazards of concurrent programming, they all ultimately boil down to this issue of shared mutable state. So if you have multiple things going on, as long as there's no mutable state, you're fine for the most part. I mean, there are other things to think about in terms of caching and so on, but you're in pretty good shape from a correctness point of view. If you have shared mutable state, that's when things get tricky. So reduce assumes that it's dealing with something that's immutable. And if that assumption is violated, then bad stuff happens. So let's take a look at an example. So here's our factorial program, which you can see at this link. And what you see here is we've got a stream. So we have a stream. This is a sort of a primitive stream. And we've got a closed range from 1 to n. So we're generating n of these things. They're going to run in parallel. And then this is what's going to happen. So we're going to do a reduction. And we'll talk about the couple of different variants for this reduction. All right. So first thing to note is that when you run the parallel stream on this range, what happens under the hood is it actually chunks it up into smaller pieces, right? So we start out with a range of the full range, and to make it easy, to make it fit on one slide, let's say it's 1 to 8, right? We're going to compute 8 factorial. If it gets much bigger than that, it goes off the end of the screen. So we have a range from 1 to n, and then that gets split up into a range from 1 to 4 and a range of 5 to 8. And that's, of course, the job of the splitterator to do that splitting. And then we end up with yet another split where we have a range of 1 to 2, 3 to 4, 5 to 6, 7 and 8. It could split further, but I'm going to stop at this point just because I wanted to keep it on one slide. So then what happens is each of these ranges is now run in parallel, but each of the ranges is processed sequentially, if that makes sense. So it's going to do this reduction, right? It's going to reduce the value a times b. So it's going to say a times b, which equals 2 for this case, which equals 12 for that case, which equals 30 for this case, and which equals 56 for the final case. So that's what's called the accumulator phase. So it's kind of accumulating the results of doing the processing. So now we have partial results, which you can see are 2, 12, 30, and 56. Any questions about that? All that processing is done sequentially, right? In parallel. So all the sequential processing takes place in parallel, which sounds a little funny, but that's what it's doing. Then what happens is we do the reductions in parallel, right? Sorry, what we're doing is now we're reducing the partial results. And this is combining immutable values to create a new immutable value. So these are immutable values, 2, 12, 30, 56, and so on. And now we're going to take the results of these two things, and we're going to reduce them. So 2 times 12 is 24. 30 times 56 is 1,680. Just trust me on that. And then if we multiply these things together, yet again, we'll get 40,320. So these are the results of reducing the partial results. And that's what this processing is right there. Any questions about that? Okay, so this is what's happening when we're using the 3-parameter version of reduce. So the key thing is that the expectation is that this whole thing is immutable. These are creating values that themselves are then multiplied together in an immutable way. Collect, in contrast, mutates an existing value. And this is a very different kind of beast, because that means that you have to have something that's capable of being changed. You're changing an object. Whereas here, we weren't changing an object with reduce. We were creating a new object that was the result of applying the reduction and creating a new immutable object. So we don't actually mutate anything. We just go ahead and create a new thing that's a combination of something else. So collect mutates an existing value. So the analogy to think of is like Play-Doh or whatever, where you can mold it. So here's an example of that. So here we're going to go ahead and have a little program, it's shown here, which is going to go out and read all the words, all the works of Shakespeare, and it's going to break up the works of Shakespeare into their distinct words. So we're going to have all the words, not distinct words yet. So this is going to go ahead and get all the words of Shakespeare, and then in parallel, it's going to collect it and store it in a new tree set. So tree set, as you might recall, is a binary tree that uses a red-black implementation, so it's a balanced binary tree, and it has no duplicate values. So every value in the tree set is unique. So what it's going to do is it's going to end up with a unique set of words in Shakespeare. And if you run the program, you'll see what it does. Okay, so what it's going to do is it's going to go ahead and take all the words in Shakespeare, and then it's going to split that into half the words in Shakespeare and the second half of words in Shakespeare, and then it's going to break it up into the quarter of the words of Shakespeare, and so on and so forth, till it reaches some minimum size, and it says, okay, uncle, I've got it to a point where I can start doing processing in parallel. In this particular case, I think if you look at the program, it like uppercases all the words or something like that. Just does something or other here that's, just burns CPU time. And then it goes ahead and it collects all the pieces back together. And in this particular case, collect is a container that will accumulate the results that it's producing. So it's going to be adding the results of the merging of these values. Now, it turns out in this particular case, in the particular case of the tree set, that's pretty expensive. Merging these things back together is relatively expensive, and that's because it has to keep them in sorted order, right? So it's not just like appending something at the end to join them. It has to merge them, and so that's fairly expensive. If you run the program, you'll see it takes a non-trivial amount of time to do that. So one thing you can do is you can use what's called a non-concurrent collector, and this is an example of a non-concurrent collector. This basically converts this stream into a collection, which is a tree set. And we'll talk about non-concurrent collectors shortly, and you'll see what they do is they actually end up having a separate collector instance per thread that's doing the processing. And as things get merged together, they're never having the merging taking place in more than one thread at a time. So it's thread safe. But you actually have multiple collectors, or multiple collectors, multiple mutable containers, let's call them, that have to be merged together. There's another way of doing things, which is something that's called a concurrent collector. And here's an implementation. This is also shown in the example. We'll talk about this later. A concurrent hash set collector, and that should be a capital C, has a way of being able to do all this concurrently. And it actually eliminates the need to do the merging of partial results because it simply updates the concurrent result collector as the processing is taking place. So this actually has a different implementation. And as you'll see, if you run the program, in some circumstances, this can actually be a lot faster for parallel streams than would be the case of using non-concurrent collectors. Even though they both work fine, the concurrent collectors may run faster in some circumstances. Okay, so we'll talk more about that here in a second when we talk about how to implement a collector. There's a whole bunch more discussion about reduce versus collect that appears here online. I strongly recommend you take a look at it. It's by my friend and colleague, Angelica Lanner, or Angelica, I think her name is pronounced. And she's very, very knowledgeable about a lot of things related to many things, but Java and Java streams and Java 8 is another one of the things she's great at. So this is a fun tutorial to watch. Here are some of the things that she talks about. So one of the points she makes is always test your streams as parallel streams, even if you don't intend to use them as parallel streams, because you will just discover bugs in your code. And here's an example of a bug in the code. And this is so weird. If you run this example here, you'll see this. I did it so you could see what it does. And it is horrible, believe me. When you run it with a parallel stream, really bad things happen. Here's what we're trying to do. We're trying to take a bunch of words, so we have all the words in Shakespeare, for example, and we turn that into a stream, and then we're going to conditionally enable parallelism. And this is something a lot of people don't know you can do. I only found out about it a couple months ago. You can actually take a stream and you can conditionally make it a parallel stream. So you don't have to hard code its parallelism property into the stream itself. You can turn it on and off based on a flag. So we pass a flag in that says, is it parallel or not? If it's parallel, we call the parallel method, and that makes this stream parallel. And then what we do is we go ahead and we do reduce. So what we think we're doing here is we think that we are going ahead and making a new string builder, and then we're going to go ahead and append the strings together using the string builder. Now, if parallel is false, in that case, we're not doing a parallel stream, so it's a sequential stream. And everything works just fine. So no problem at all. It'll go ahead and append everything together, and you end up with a single reduced string of all the stuff that you need to have at the end. Conversely, if you use parallel, then this code will behave horribly. And the reason for that is that reduce thinks it's dealing with immutable objects, objects that are able to be used in multiple threads because they have no side effects, because they're immutable. Once you create them, they never change. But in fact, a string builder is actually something that creates internal state, and every time append is called, it sticks the new string at the end of the string builder's internal state, right? So you have like a buffer internally, and string builder just puts things at the end. It kind of grows it out as append is called. Well, not surprisingly, if this is called in a parallel stream, reduce expects to have the object it's working on be immutable, so it doesn't do anything to lock or protect the results at all. So as a result, you'll end up with chaos and insanity. And if you try running the program, you will see chaos and insanity. It's pretty funny. It just gets wildly incorrect very fast. Even with just a very small number of things that are running in parallel, it goes berserk. And this is just showing you can turn the stream on and off to parallel. Okay, so what's the fix to this? What's the way to get around this? Does anybody know? If you end up with, if you're maintaining software, somebody hands you this code and says, when I turn parallelism on, it fails in a bizarre way, what should your approach be at that point? Okay, so one thing you could do is you could use immutable operations or synchronized operations. So one thing you could do is you could write some kind of wrapper for string builder called synchronized string builder. That probably would work, although it would probably be rather slow. Another thing you could do is you could replace the use of string builder with a string, right? You could use string operations. So you could say new string, and you could say, A plus B using the plus operation. And that'll work. Why will that work? Does anybody know why that would work fine? Because string is a mutable object, right? So that will work okay. That'll also be really slow. Why will that be really slow? Right, it'll make copies of everything. So it'll be fast. It'll be slow. It'll be thread safe, but it'll be really slow. So what's a better approach to use? Collect, exactly. Because collect is built to work properly when dealing with mutable result containers, whereas reduce is not. So that's the secret there. Okay, another tricky issue. This is very subtle. Beware of issues that are related to association and identity. So and this is also illustrated in this example. So it turns out that addition and multiplication are associative. Everybody remember what that means? So associative just means if you do, A op B gives the same value as A op or B op A, and you can also group things together within parentheses. I guess that was commutative. And then associative is you can say A times B plus C is the same as A times B times C, right? So the way you group things together, you get the same result. So multiplication and addition are associative, but subtraction and division are not. And so if you do them in a different order, then weird things happen. And so what will happen here, if you try to do the following, the code here that's called test difference reduce, and you try to run this code, which uses subtraction, it'll sort of work, with the emphasis on sort of work, if you use it in sequential mode, except that the identity value is tricky. For trying to figure out what the identity value is for subtraction is hard. Let's leave that aside for a second. But irrespective of that, if you turn on parallel streams, you will get a very different result than if you run this with sequential. They both actually turn out to be wrong, but they're wrong for somewhat different reasons. So the main problem is that this is that subtraction is not associative. And the way in which the parallel stream does the reduction in that little tree format I keep showing you, the combinations of the subtraction are not going to run in the sort of a coherent way from left to right. So they may run in different orders. And since it's not associative, you'll get the wrong results. Okay, so that's basically the problem with the associativity issue. And the other issue here is that 0 is not a good identity value. Let's talk about identity. So the second problem we have, let's see. So the second problem we have here is related to identity. So in identity, the identity of an operation is defined as identity op value equals value. And it also should be the case that value op identity equals value, right? So either way you do it, you should end up with the same result. That's why subtraction doesn't quite work for this, because it's not the same if you do it in the different orders. So if you end up giving the wrong identity value here, then you're going to get incorrect results. And if you run the test again, you'll see that. So for addition, the identity value is obviously 0, because 0 plus anything returns anything, right? And anything plus 0 returns anything. And so if you give this value, say 1, you'll get the wrong result. Likewise, if we were to do test product, which is also shown in the test program, you'll see how in that particular case, what you get if you have, 0 times whatever doesn't return whatever, it returns 0. So make sure that the identity for multiplication is 1, make sure that the identity for addition is 0. And that's kind of subtle, and you can also get yourself into trouble if you try to do anything other than put identity here. And that's because when this thing is run in a parallel stream, you'll see in a second that you end up with multiple copies of the shared result container. And if they all start out with some value other than the identity value, which is 0 or 1, bad things will happen with the final results. Okay, so these are some subtleties. This is really not that complicated as long as you know the rules, but the system will not save you from yourself. So if you forget and use subtraction in a reduction, or you put the wrong identity, nothing will come back and tell you, you've got a bug, your program is not working. You'll just get the wrong answer. You may get it very quickly, because you may have a parallel stream that will very quickly give you back the incorrect answer, but it's still the incorrect answer. All right, let's now talk about how do you implement concurrent and non-concurrent collectors. And this is an interesting topic that is not really very well documented most places. I'll give you some pointers to some places on the net that talk about this, but in general, what we're going to cover here is somewhat black art. So basically, a collector is an interface whose implementations are used to accumulate input elements into a mutable result container, because that's what a collector is, right? It mutates stuff. And it turns out that collector implementations can either be non-concurrent or concurrent, and what controls that are their characteristics. And in particular, there's a particular characteristic called concurrent, which is, again, somewhat mysterious, and it's hard to tell just by reading the documentation what the heck this thing is good for. This distinction between concurrent and non-concurrent is really only relevant for parallel streams. Obviously, if you have a non-parallel stream, a sequential stream, then just go with a non-concurrent collector, because anything else you do is ridiculous because you're not running concurrently. But this distinction of concurrent and non-concurrent really matters when you're dealing with parallel streams. And the other thing to remember, which is also very confusing, you would think, oh gosh, non-concurrent collector, gotta only use that with sequential streams. Concurrent collector, gotta use that with parallel streams. Well, just to make it confusing, that's not the case either. A non-concurrent collector could be used quite nicely with parallel streams. A concurrent collector, of course, can be used nicely with a parallel stream. They both work, they just work differently in terms of their processing time, but and sometimes the order in which things happen, but the correctness should be the same. So we're going to focus, and the reason why I have the Shimmer non-dairy floor wax is because if you ever watch this famous Saturday Night Live episode, they say, Shimmer, it's a dessert topping, it's a floor wax, right? So it's two things in one. So a collector, a non-concurrent collector, is useful for sequential streams. It's useful for parallel streams, right? It's two things in one. In all this discussion we're about to have, we're going to focus on parallel streams. We'll ignore the non-parallel streams because it's just not interesting. So a non-concurrent collector operates by merging subresults. So there's some implication that we're going to have separate collectors that are going to work, and then they're in one per thread context, and then they're going to be merged together when they're all finished. Now, just as always, the input source is partitioned into chunks. That doesn't change. Each chunk is collected into a result container. Maybe a better way to say it is a sub-result container, right? So it's collecting things in whatever container you have designated, which could be a list, it could be a map, it could be a set, whatnot. And in the context of parallel streams, which is what we're talking about here, then different threads will operate on different instances of these intermediate result containers. So everything that in this thread will end up putting stuff into one result container. Everything in this thread will put something into another result container. Everything in that thread will do that for yet another result container. Those are all different intermediate result containers. And then as things go along, those sub-results, or those intermediate results, will be merged together to form a complete result by the time everything's done. And of course, that's done in a tree-like fashion, so it goes together, sort of in log-n steps. And because of the fact that the parent thread always does the merging, so there's never any issues of two threads trying to merge something together with a non-concurrent collector, then there's no need for any synchronizers. So we don't have to have any locks in the code to do that. So this is actually very easy to write, although we'll see that there's some situations where it doesn't perform very well. And so even though this process that we just talked about will be safe, thread safe in the sense that it will not have corrupted data, and it's also capable of preserving order if that's important, merging costs might be costly for certain kinds of containers. And those would be things like maps and sets, where merging stuff together takes a fair amount of time because you have to take all the contents of one intermediate result container and all the intermediate result container contents from another intermediate result container and bring them together into a new container, or merge one into the other. So the point there is that could take a fair amount of time to do. It's not just like tacking it onto the end, which is what it would be if it was a linked list or maybe an array. Okay, so that is how the non-concurrent collector operates, and I'll show you an example of how you'd write one in a second. Concurrent collectors behave a little differently. So as usual, we pull out our Highlander reference because there can be only one. There can only be one concurrent result container. And all the elements that are being produced as a result of doing the parallel computations will all be put into that single result container. So they all kind of get pre-merged. You're not merging partial results. You're just merging results into a single container. So as usual, the input source is partitioned into chunks, and then the processing takes place. And as the processing finishes, rather than having sub-results or intermediate result containers where the results are going to be merged, instead everything just gets plopped directly into the concurrent result container, which is typically something like a concurrent map or concurrent set or something like that. And the different threads in a parallel stream will all share this one result container. Now, the implication, of course, here is that this result container had better darn well be efficient to add stuff into, because if it's inefficient, then you may have some challenges. And the good news is that the containers that come out of the box with Java 8, the typical ones you would use for this, would be things like concurrent map, which is super duper optimized, concurrent hash map. Concurrent hash map, which is super duper optimized for multiple threads working together. And even though there's a lot of writes going on, it tries to be clever about how it does that. So it partitions the writes across the hash table. So hopefully there will be limited amount of contention while that's taking place. So it's actually relatively fast. And if you run the test program, you'll see how it works. And it is faster. Okay, so the good news is there's no need to merge these intermediate subresults. And the other issue, of course, is you really can't easily preserve encounter order because it's just happening in the concurrent way in which it's happening. Okay, so why would you use a concurrent collector? You may use this because it's often, not always, but often going to perform better than a non-concurrent collector for collections where merging costs are high. So if you have a situation where it's expensive to merge stuff, then that's what you want to use. And there's a nice example, which we'll talk through here in a second, that I have in this test program called concurrent hash set collector. So a concurrent hash set collector is just a little adapter that I wrote that adapts the concurrent hash map. And so it basically uses a hash set instead of a hash map. And so you can take a look and see how that works. It's pretty cool. But we'll use that as a running example here to show how all this stuff works. So here's examples of where it turns out to be very useful. So concurrent hash map has all these special optimizations to try to minimize contention when multiple threads add elements into the hash map, or the hash set, which is just a variant of hash map. And so if you don't have elements that hash to the same location, they can run in parallel. If you do have elements that hash to the same location, then you can be clever about how you add them so that you minimize contention and so on and so forth. In contrast, if you were to use a more traditional data structure like a synchronized map to do this, that would be very expensive. And the reason it would be expensive is because they have a single lock that protects the entire collection. And so you'll get with a lot of contention here when multiple threads try to write to it, because they all wait for that single lock. So that's kind of an aside, and we may have a chance to talk later about concurrent hash map. Concurrent hash map is super duper cool, and there's some really good articles online that explain why it's so optimized for concurrent access. Okay, so let's talk about the collector interface. So there's an interface called collector, and there are 3 generic types that are in collector. One type is type T, that's the first generic parameter, and that's the type of object or objects that are available in the stream that we're collecting. So if we're collecting a stream of integers or a stream of longs or a stream of search results or a stream of employee records or whatever, that's what T is. That's the type T that we're working on. A is the type of mutable accumulator object that's going to be used to actually store the results, and that we're going to use, as the collector to collect all, the collection to collect all this stuff. So if we're doing it for a concurrent collector, it might be a concurrent hash set. If we're doing it for a non-concurrent collector, it could be an array list. It's basically whatever it is we want this thing ultimately to create when we're done. Sorry, not to create when we're done, to accumulate. And then the final thing we have is R, which is the final type of the result, which sometimes is the same as the type of the accumulator. So it might be a concurrent hash set, or it might be an array list of type T, but it doesn't have to be. And so you can actually have different types returned as the return type than you're accumulating. And it's the job of something called the finisher function, which you can see up here, to do that transformation if necessary. Now, as we'll see, when it's not necessary to do a transformation, you can make it be the identity finisher, which means there's nothing to do at the end, you're just done. If you don't if you don't have things be the same type, then the finisher has to be whatever converts it from the intermediate accumulator form into the final form. And in fact, just as a quick side note, the future collector that we talked about, futures collector that we talked about, that's used in your assignment 3A, that's an example of something that has a different result type, completable future of blop from the accumulator type, which is basically going to be a collection of some kind. Okay, so those are the three main types you pass in. Then there are 5 methods that are defined in the collector interface that utilize these types in various ways. We'll start with the last one because you kind of need to understand that in order to understand some of the other distinctions. So there's something called characteristics, which you can think of as kind of like flags that indicate what kind of a collector this thing really is. And these flags are used internally by the streams framework to decide how to run the computations that take place as this whole thing is going on. And so this actually has a big impact on the behavior and the performance, in some cases, of your collector that you might write. So one property is unordered, and that simply says the collector doesn't need to preserve in counter order. So if you don't really care the order in which things are put together, just leave it unordered. And that way it'll be unordered. If you don't set unordered, it'll assume order, and it'll go ahead and do it in counter order. In general, a concurrent collector should be unordered, but a non-concurrent collector could be ordered. Actually, in many cases, it doesn't really matter because it's just as fast to do it in the order as in unordered, but in some cases it matters, and concurrency is a good example of that. The next flag is identity finish. And this basically says, is the finisher going to do any transformations to the results of accumulating and combining all the various elements? Or by the time we're done accumulating and combining, is the finisher a no-op? So in some cases, if the finisher is the identity function, it can just be a no-op. It can just return null. And as a general rule, a concurrent collector should be identity finish, whereas a non-concurrent collector could be. Depends on what it's going to do. Then the next question is concurrent. So what this says is, does the accumulator method get called concurrently on the result container? And if the answer is yes, in other words, if it's a concurrent collector, then it has to be the case that the result container is synchronized in some way, because you'll be accumulating into a common shared result container from multiple threads, and it darn well better be synchronized, otherwise you're going to have corrupted data. So that's what concurrent means. And so a concurrent collector, should be concurrent, right, of course, and a non-concurrent collector should not be. Obviously, if it's set as concurrent, it's not non-concurrent, it's concurrent. Another thing to note is if you have a concurrent collector, the combiner method will not be called because there's no need to merge subresults because they're all just going directly into the collection. And the key thing to remember here is a non-concurrent collector can be used with either sequential or parallel streams. Not entirely obvious when you first read the term why that's the case, but it is the case. And so you have to decide which to choose. And if you run my example program, you'll see both being used, and you'll see the performance consequence of using it. Here's a simple example, just showing how you could create a characteristics set with all the characteristics set. And of course, if you wanted to leave out some, you could just remove the ones you didn't want. And if you want to have them all, take the default, which is non-concurrent, non-identity finish, and non-unordered, just return null. So just return the empty set. So there's no characteristics set at all. All right, so those are characteristics. That's going to set the properties, the behavior of the collector. The next topic here is, what's the supplier? Well, the supplier is basically a factory method that returns an instance of a supplier that will be used to initialize or generate an empty results container. So let's say, for example, we're doing a non-concurrent collector. In that case, we would return, say, array list new. So if we're doing an array list collector, we would simply return the new array list instance using a constructor reference. So that's just going to return a constructor reference to make yourself a new array list. And that'll get called by the framework when it needs to initialize the internal result container. Conversely, if we're doing a concurrent collector, then we probably want to return something more interesting. So in this case, we're going to return a new concurrent hash set. And that's going to have one result container that's shared by each thread in a parallel stream. Any questions about that? Okay, so then we have the accumulator. And accumulator is the thing that's going to add a new element to the result container. And so think about what's happening, right? We've got a stream of elements. We've created ourselves a supplier. That supplier is going to be accumulating elements of the stream and putting it into the result container. So that's what it's doing. And so here's a very simple one. If we have a non-concurrent collector, we could just use, say, ArrayListAdd. So in that case, the collector's method should not be synchronized because it's never going to run concurrently because it's non-concurrent. But if we're going to be using a concurrent collector, then we need to make sure that we use an accumulator that will be thread safe or synchronized. So concurrent hash set would be an example of that. So a concurrent collector's methods must be synchronized. Any questions about that? So we got accumulators. They could be concurrent, or it could be thread safe or not thread safe. It all depends on whether it's a concurrent collector that matters. All right, so accumulator is what's used as we're creating this thing. Now, if we have a non-concurrent collector, then we've got to have this merge phase, this combination phase. And the combiner is basically going to be a factory method that returns a function that merges two results containers together. So if we have a non-concurrent collector, so this should say if this is a non-concurrent collector, then we need to be able to have code that merges the elements. So this is how you merge together two array lists. So you take one array list and another array list, and you add another to one, and you return one. This comes back as that you return the leftmost one. So that's how you would do the combiner if it's a non-concurrent collector. If it's a concurrent collector, then the combiner method is a no-op because we're just accumulating everything into the collector directly, and there's no need to combine it later. So you can just return null. So it's basically a no-op. And then finally, the finisher, if there is one, returns a function, it's a factory method, that converts the result container to the final result type. So if it's a non-concurrent collector, then typically in a non-concurrent collector, it'll just be the function identity. It just returns the internal container, result container, that has been accumulated and combined into. You can also do much more interesting things. If you want to see an example of a much more interesting thing to do, take a look at the futures collector that we're using in assignment 3A, where it's actually doing something interesting in the finisher, where it's essentially creating a completable future that waits for all the other completable futures to finish. So that's much more interesting. But a lot of times it's just identity. If you have set the identity finisher flag, I think it's actually identity finish flag, in that case you just return null. So it's a no-op. That method will not be called. That of course assumes that whatever you've accumulated and combined into is the final result. Okay, so that's the end of the discussion about collectors. Probably more information than you necessarily need to know, but it's good to be aware of this stuff because at some point if you ever have to implement one, now you'll have a place to go to learn what the various